In this video, we're going to go through 4 different multiple choice questions on gravitational fields. So there's some on kinetic energy here, there's gravitational field strength, the gravitational force equation, as well as relating time period to the radius. So yeah, let's get started with this one on the top left. So it's given you a radius r and a density rho. It's asked you to find the gravitational field strength when the radius is doubled and the density is doubled. So first of all, in terms of planets, we know that's the radial field, so we use this specific equation for gravitational field strength. Now, a change in radius will affect the denominator here, but how does a change in density affect each of these variables? Well, this is constant. This is unaffected by density. It's actually the mass that's affected by the density. Now, the mass of any spherical, or just any surface actually, is just the density multiplied by the volume. Now, because we're talking about a planet here, which is spherical, we can replace the volume with 4 over 3 pi r cubed, because we know that's the equation for the volume of a spherical surface. And then we're multiplying that by rho. Perfect. That means that this equation here essentially becomes gravitational constant multiplied by 4 over 3 multiplied by pi r cubed times rho, all divided by capital R. Now r cubed can cancel out with r, leaving you with r squared. And so I'm just going to tidy this up a little bit, but we can say this is r squared rho. And that's what this g is initially equal to when there's a radius capital R and density rho. But what happens if we double the radius and double the density? Well, let's see. When we double the radius, so gravitational field strength, gravitational constant is unchanged, 4 over 3 times pi times, but the radius is being doubled, and we square the doubled radius. On top of that, the density is being doubled. Now 2 squared is 4, so this is like 4r squared multiplied by 2 rho, which is 8r squared rho. Because these variables are constant, and this is 8 times larger than this, that means that the value of g will be 8 times larger. I'm just going to double check to make sure I've done this all correctly. So 4 over 3 times pi r cubed rho. Oh, no wonder why. I thought something looked a little bit dodgy. When you substitute in r cubed into this top and you divide by r squared, it actually cancels out to give you just a power of r. So it should be r to the power of 1. Sorry about that. So this should be 2r to the power of 1 multiplied by 2 rho, which is then 4 times as large. Yeah, I was just thinking, I did this question beforehand and I got it, that is 4 times as large. And so g will be 4g for this specific question. Yeah, sorry about that. Moving on, it tells you that the distance between Sun and Mars varies from this distance between them and this distance between them. When they're at their closest, so at a distance of 2.1 times 10 to the 11, the gravitational force between them is F. What's the gravitational force when they're the furthest apart? So when the value of R is now 2.5 times 10 to 11. Well, how does force relate to the distance between the masses? Well, we know F equals gmm over R squared. Because g is the gravitational constant, the two masses, they're unchanged. We say that the force is being related to the square of the distance between them. Or we can say that force is equal to a constant divided by r squared. Multiplying r squared to both sides, we get force times r squared is equal to that constant. Great. That means that the force of the first force multiplied by the distance between them squared is equal to the second force multiplied by the distance between those squared. We're trying to find the gravitational attraction force, F2, when they're at this furthest apart, because we want the force afterwards. So that's equal to F1 r squared over r2 squared. F1 r squared over r2 squared. Now F1 is just this initial force when the distance between them is at their closest, 2.1 times 10 to the 11, and you square all of that. And you divide that by when the distance between them is the furthest, which is 2.5 times 10 to the 11, remembering to square that as well. Squared. And then what you get is this whole thing here equals 0.71. So this just becomes 0.71 f, meaning that at their furthest distance apart from each other, the force between them is 0.71 times as large as their closest distance together. Great. Moving on to this next part of the question, it's asking for the kinetic energy of particle X. So it's told you that the planet has a mass of m, and this little satellite has a mass of little m. Now the kinetic energy of any particle we know is just a half times its mass multiplied by the velocity squared. Now the velocity of the particle is due to the gravitational field, and actually there's an equation for it, which is that v is equal to root gm over radius. This is given to you in an exam. Squaring both sides, we get v squared is gm over r, and multiplying that onto this whole equation here, we get that the kinetic energy is just a half times mass multiplied by g times, be careful of the different masses, because this mass is the mass of the planet itself, whereas this little m is the mass of the satellite, gm over r. So the numerator just becomes gmm, and then the denominator becomes 2 times r, which is 2r. So it'll be option A. Great. Now here it's asking, how does the time period relate to radius graphically? So there's Kepler's third law, which tells you that the time period squared is proportional to the radius cubed. What that means is that the time period squared is equal to a constant multiplied by radius cubed. If you remember direct proportion from GCSE maths, you can replace this sign with an equals constant. Okay, let's apply logs to both sides and see what happens. Because the one that doesn't have log applied to it, t r to the power of 2/3, if you do cube root every term, we get that t to the power of 2/3 equals k to the power of a third multiplied by r. So yeah, this itself won't give a straight line, whereas t to the power of 2/3 against r would. So when you apply logs to both sides, let's do it to this side first. Log of t squared equals log of k r cubed. If you do A-level maths, this will be a lot easier. There's a rule that tells you can take the power as a coefficient, so you can write this as 2 log base t equals, we can actually split this up into 2 separate logarithms. We can say it's log of k plus log of r cubed, because when you multiply, when you add logarithms, you're multiplying the insiders of the logarithms. So we can say this is log k, and then we can also use that power rule again here, plus 3 log base r. And what you can actually see is that this is almost in the form of y equals mx plus c, if that makes sense. Now this is important because it tells you that y can essentially be replaced with log base t, and x can essentially be replaced with log base r, in which case the gradient will be a constant value of 3, which would lead to a straight line graph. So we want a graph of log base t on the y-axis and log base r on the x-axis, which is option C, because that will give you a gradient of 3 relating it to y equals mx plus c, which is the equation of a straight line. So quite a lot of variety of questions in here. If you have any questions with it, just let me know in the comments. Otherwise, yeah, thanks for watching the video, and be sure to subscribe. I'll post more content like this very soon.